In this example, we are going to be deriving the equations of motion for this beam. We're comfortable in lumping the mass of the beam at 3 equally spaced locations along its length. And in the process here, we're going to be deriving the inverse of the stiffness matrix using the influence coefficient approach, that is, finding the flexibility matrix. In the end, we're also going to come up with a mass matrix and then show how these two matrices together can go into representing the equations of motion for this beam. We're going to use this equation u of x, which is taken from strength of materials, for finding the deflection of a beam due to some point load F, and that point load is going to be at a position A, and we're going to be using this equation for any location to the left, that is x less than A. And so what I'm going to do is start out on the far right side, and I'm going to first apply my unit load at 3. In other words, this corresponds to A equal to the length L of the beam. So here's the picture. So with this applied force F of unit magnitude, the deflection under that load is what we're going to be calling A33. The deflection at 2, due to the load at 3, is there, and the deflection at 1, due to the load at 3, would be that deflection of A13. Using that equation, A13 with A equal to L is equal to U at L over 3, like this. So it's putting in A equal to L and X equal to L over 3, I end up with 1 over 6 EI times the quantity 2L cubed minus 3L squared, L minus L over 3, plus L minus L over 3 squared. And combining those terms gives me 8L cubed over 162 EI. Keeping the load at the same location at 3, we're going to now calculate A23, which is the deflection at 2L over 3. And that will be, again, me putting in those numbers for A and for X. This is 1 over 6 EI, 2L cubed, minus 3L squared, times L minus 2L over 3, plus L minus 2L over 3, that quantity squared. And combining terms, I end up with a fraction here of 28L cubed over 162 EI. Still keeping the load there at 3, I calculate the deflection at 3, so that's U at L. So that's going to be 1 over 6 EI, 2L cubed, minus 3L squared, L minus L, and then plus an L minus L. So this number here ends up being 54 L cubed divided by 162 EI. Now, by reciprocity, by the fact that our flexibility matrix is symmetrical, by reciprocity, I know that A13 and A31 are the same. And that, of course, is, as we calculated above, 8L cubed over 162 EI. And reciprocity also gives us that A32 and A23 are the same. And as we had above, that's 28 L cubed over 162 EI. So with one application of a force, we have picked up, what, 5 other terms. Now what I'm going to do is move my applied load from 3 over to 2. So apply a unit load at 2. In other words, my value of A is going to be at 2L over 3. The picture might look something like this. Where the force is applied here at 2L over 3. The deflection right underneath the load, that's going to be A22. The deflection out here on the end will be equal to A32. And the deflection at 1 is, by the name we've given it before, that's A12. So let's calculate A12. With A equal to 2L over 3, A12 is going to be U at L over 3. So this is going to be 1 over 6 EI. 2 times 2L over 3 cubed minus 3, 2L over 3 squared times 2L over 3 minus L over 3 plus 2L over 3 minus L over 3 cubed. So we multiply it out that, we put it over a common fraction, common denominator, we get 5L cubed divided by 162 EI. The deflection under the load, A22, that's going to be 1 over 6 EI. 2 times 2L over 3 cubed. Then we have a 2L over 3 minus 2L over 3, so that's a 0 in these last 2 slots. So this number, the 2 position, the flexibility matrix, is 16L cubed divided by 162 EI. By reciprocity, we have the A21 is the same thing as A12, which, as we just found above, is 5L cubed divided by 162 EI. So we only have one more to go. We're going to move the unit load over to 1. In other words, our parameter A is going to be equal to L over 3. That's the location of the load. We know that A11 is the displacement at L over 3. So that's 1 over 6 EI. 2L over 3 cubed minus 0 plus a 0. And so that's equal to 2L cubed divided by 162 EI. So we have computed all 9 terms, our flexibility matrix A, just repeating what we have just derived is 2, 5, 8, 5, 8 down, 16 and 28 across, 28 down, and the 3, 2. In the 3 position, we have 154, and that all gets multiplied by L cubed divided by 162 EI. And this is the inverse of the K matrix, which in the notes we're calling this the flexibility what are the equations of motion? How would we use this in determining the equations of motion? Well, what I'm going to do is first write down the kinetic energy T. T is 1/2 my dot squared for each one of the three masses, where the y's are the transverse displacements of those particles of mass on that beam. So let me maybe draw a picture of that just to make sure that we understand what that means. For a general deflection of this beam, the dynamic response of the beam, whatever that ends up being, at location 1 is y1, at location 2 is y2, and whatever we have here for the deflection, dynamic reflection at 3 is going to be called y3. So from this, it is very easy to see that our mass matrix is going to be simply the masses of each one on the diagonal and zeros on the off diagonals. I don't think it says in the problem statement what the masses are, so let's assume, for the sake of deriving equations of motion, that the masses are the same. So what the Lagrange's equations would give us is this: m y double dot plus k y is 0. So we know this. K we don't really know. We know k inverse. Why not pre-multiply our Lagrange's equations by the inverse of k? So we have the inverse of k times m y double dot plus k inverse k y is 0. We know that any matrix, you take the inverse and multiply by the matrix itself, we end up with the identity matrix as such. So if I multiply k inverse times m, what I get is m L cubed over 162 EI. The 3 by 3 matrix here, 2, 5, 8 across, 2, 5, 8 down. The 2, 2 position being 16. The 2, 3 is 28. The 3, 2 is 28. The 3, 3 position is 54. Y double dot plus y is 0. So this is one way to actually get the equations of motion without really having a good way to represent the stiffness of this beam. We didn't do it by the traditional way. We didn't write down the potential. What we did was we used the influence coefficient approach to get the inverse of k, and then use the inverse of k to come up with our equations of motion.